Hey everyone, Matthew Sabri here. I got asked whether or not my developing Kubernetes integrations for the on-premises cloud talk was recorded during All Things Open 2025. Unfortunately, it was not. I don't think any of the cloud track talks were recorded this year. So here I am recording it a couple weeks later because I got asked about it a couple times and I wanted to have this artifact for you all. So let's dive in. Developing Kubernetes integrations for the on-premises cloud. This is me, Matthew Sabria, and I presented this at All Things Open 2025. So the on-premises cloud is very interesting because we have so many public clouds out there, AWS, GCP, Azure, but what is the on-premises cloud? And spoiler alert, obviously you see from my title slide, it is Oxide, the on-premises cloud. Although this is not an Oxide product pitch, this is just how a developer experience of developing Kubernetes integrations for such an on-premises cloud, right? A computer that's on-prem, but has these sort of cloud APIs that you know and love. So Kubernetes Pop Quiz. Does this work in your cluster? This is a manifest that creates a service of type load balancer. Does it work in your cluster? How about this one? This one creates a persistent volume claim and it's requesting a 1 gigabyte volume. What about this? This is the node manifest showing that a node has a taint of node.cloudprovider.kubernetes.io/uninitialized, and that taint has the effect of no schedule. If you don't even know what that is, that's fine. We're going to talk about this because these are things that people creating Kubernetes integrations need to think about. So here's what we're going to cover. We're going to cover what Kubernetes integrations exist, and we're going to understand that Kubernetes integration ecosystem. We're also going to cover which integrations Oxide built and how we chose to build these integrations and why. And we're also going to cover how was the integration experience, right? The lessons learned and problems encountered. First, we'll give a Kubernetes overview. This is what a Kubernetes cluster generally looks like in an architecture diagram. And I took this straight from the Kubernetes website and I ran it through AI to change the colors and make it a little bit better. You can see here a Kubernetes cluster generally has a control plane and a worker plane. So you have control plane nodes and you have worker nodes. And the control plane nodes, they generally run the Kubernetes services themselves. The Kubernetes API, the scheduler, some controller managers, and the worker nodes, they generally run the kubelet and a container runtime interface so that you can run containers, such as Docker, CIRO, Containerd, whatever else is out there. We'll come back to this diagram a little bit, but this is basically the overview. You have a control plane and worker plane. So the control plane components are generally this. You have the Kubernetes API server. You have etcd, because you need a place to store that Kubernetes API data. You have the kube scheduler, which monitors the node resources to know where to schedule pods. You have the kube controller manager, which runs Kubernetes controllers that implement default behavior for built-in Kubernetes resources. And then you have this optional cloud controller manager component, which runs controllers that can integrate with an underlying cloud provider, for example, Oxide. Worker components, on the other hand, are generally the kubelet, which ensures that pods are actually running on the nodes that Kubernetes told them to run on. The kube proxy, which kind of maintains that network rules to implement service resources. And you have the container runtime, like Docker Engine, Containerd, and this is responsible for actually running the containers on a node. Kubernetes has a couple of different integration points, places where you as a developer can develop integrations for Kubernetes. Here's an example of the architecture of integrations here. You can develop Kubernetes integrations for kubectl, you can develop API server integrations such as webhooks and emission control hooks, you can develop different CRDs or different resources, you can develop a scheduler, you can develop controllers, you can develop network plugins and device plugins, and you have all this information here, or all these places in Kubernetes where you can develop plugins. And we're going to focus a little bit about a couple of layers of this. We're going to focus on controllers, and we're going to focus on device plugins. So what Kubernetes integrations are even out there? First up, there's what's called the Cloud Controller Manager. So the Cloud Controller Manager is a control plane component, and its whole purpose in life is to run controllers to give you cloud provider specific functions. For example, to create a load balancer. This uses a standardized cloud provider interface that the Kubernetes development teams created to ease development across all cloud providers, whether it's AWS, GCP, Azure, DigitalOcean, or even Oxide. We all use the same interface to implement this controller. And here's the layer that this operates at. This is a cropped image of the Kubernetes sort of diagram I showed earlier. And this shows you that the Cloud Controller Manager runs as a control plane component, so it runs on a control plane node, and it's responsible for communicating with the cloud provider API. Let's see how. The Cloud Controller Manager interface looks like this if you look in the Go code. It has methods to initialize and set up your provider, and it also has methods to create load balancers, manage routes and instances, and these are the methods we're going to be looking at a little bit. So when you want to deploy a Cloud Controller Manager or develop one, what do you need to do? Well, you need to write a program that implements this Cloud Controller Manager interface. You need to build a binary. You need to run all of your Kubernetes control plane components with the -- cloud provider external flag. That tells the Kubernetes control plane components, hey, there is an external Cloud Controller Manager that's going to take over all of that cloud provider specific logic, so use that. Then you can deploy your built Cloud Controller Manager binary to Kubernetes, and you make sure it's configured with the right authentication to talk to your cloud provider API. For example, when I deploy the Oxide version, I give it the Oxide hostname and API token, and then you use it. You create your load balancer services, you check that nodes were added and removed. So what is this really doing? Let's show you with more of code. For example, if I have the Oxide Cloud Controller Manager deployed to a Kubernetes cluster, I would be able to create a load balancer. Now, granted, Oxide doesn't have load balancing support at the time of this recording, but this is the general end state that we're going for and why we're creating this integration now. So let's say I create that load balancer, right? I create a service of type load balancer. What happens? Well, the cloud provider, the Cloud Controller Manager, the load balancer function is called, or method is called. So Kubernetes says, hey, I see you want to create a load balancer service. I will defer to your Cloud Controller Manager because you told me that you're responsible for creating load balancers, and it's going to call this method. And this method looks like this. It's actually an interface. It returns an interface type that has all of these abilities to do things, right? All of these methods to do things. So when Kubernetes calls your load balancer method, it receives this load balancer interface back, and now it can call all of these different methods to ensure a load balancer exists or update it or whatever. And you can see here, all of these methods take a service spec from the Kubernetes API and returns, or even some like a slice of nodes to put in that service spec, and returns some sort of status or error signifying, hey, the load balancer was created. So what about instances though? There was another controller in the Cloud Controller Manager that manages instances. That's done via the instances v2 implementation. So for example, earlier I showed you this. When a Kubernetes cluster is using the Cloud Controller Manager, right? All of the control plane components are started with that cloud provider external flag that I showed you. The Kubernetes nodes are no longer managed by themselves. They defer management to this Cloud Controller Manager component. What does that mean? That means when you join a node to a Kubernetes cluster that's using a Cloud Controller Manager, it's going to be tainted with this taint until your Cloud Controller Manager removes this taint. And how does it remove this taint? Well, when a node is added to your cluster, the instances v2 method is called. That passes back a instances v2 interface, which has its other methods. And there's only 3 methods here. Does the instance exist? Is it shut down? And what's its metadata? And here, the metadata one is important because when a node joins the cluster, it'll check if the instance exists, it'll check the metadata, and that metadata will say, hey, here's the node's labels and addresses, how to reach it. When that's done, the Kubernetes controller will say, great, you've passed me successful metadata, I can remove that taint and your node is ready to rock. The Cloud Controller Manager for Oxide is at this Oxide Computer / Oxide Cloud Controller Manager repo. I have currently implemented the instances v2 controller, and that'll be improved more and more as Oxide adds more features. But I left the load balancer unimplemented because we don't have a native load balancer in Oxide yet. Now, there are things I actually can do. Thinking about this more and talking to people, I could kind of fake that a little bit and implement the load balancer controller anyway and use Oxide's external or floating IPs to be a kind of like a fake load balancer. And I actually might do that, but the load balancer component remains unimplemented for now. And as you saw earlier, there was a routes component or a routes controller in there. I opted not to implement that at all because we generally use third-party CNIs in our Kubernetes clusters. Speaking of clusters, what about the cluster API? So the cluster API is a mechanism, I guess, to create and manage Kubernetes clusters using Kubernetes custom resource definitions and controllers. Basically, if you have a Kubernetes cluster, you can create more Kubernetes cluster by applying YAML to your Kubernetes cluster. So more YAML to create more clusters. This is a pretty big integration, and it automates the entire cluster lifecycle for platform operators. And it's a very, very complex sort of architecture, really. What you're supposed to do when you have a cluster API is you're supposed to create some sort of Oxide cluster or cloud provider specific cluster, just like this. And you can say, hey, I want to create an Oxide Kubernetes cluster. Here's the resource definition. Then you're supposed to create a Kubernetes cluster type referencing that sort of cloud provider specific infrastructure reference. And then that's all the controllers in the backend read all of this data and work to make your cluster available. Again, quite complex for what it's doing, because really the end goal here is to create a Kubernetes cluster, and the cluster API just has a lot of moving parts to it. Really does. Read the spec for it. Read the documentation. So at Oxide, we chose not to implement the cluster API today, and really because of two reasons. One, there are other ways of managing Kubernetes clusters today, right? You have kubeadm, you can do Rancher, you can do Talos, you can do a bunch of other ways of managing Kubernetes clusters. And quite frankly, I don't really like the requirement to have an initial Kubernetes cluster before you can even use the cluster API to manage further clusters. So it's unimplemented today, but it might be implemented in the future. There's another plugin though, the Rancher node driver. So Rancher is a sort of a Kubernetes distribution, I guess at this point, whatever you want to call it. But the node driver specifically is a plugin that you can install into your Rancher platform, and it's going to be used to provision instances that Rancher can use to manage Kubernetes clusters. So what happens is Rancher will call this Oxide Rancher node driver plugin, say, hey, please create me some Oxide instances, and then it will use those Oxide instances to create Kubernetes clusters. This is far less complex than the cluster API because it relies on a Docker machine interface, which is just one Go interface to implement. It's a big interface, but it's still just one. So it's kind of more simple to implement than cluster API. And all you do is implement the interface, build a binary, deploy the binary to Rancher, and then use it. So what's that interface I was telling you about? The Rancher node driver interface is called driver, and it has a bunch of methods. Honestly, way too many methods, but the primary ones are here. Create means create an instance. The name is the driver name. Pre-create check gives you a way to kind of validate things beforehand, and then remove, restart, and start and stop are all self-explanatory. So how do you use this thing? Well, once I build that binary and implement the interface, I can deploy the actual plugin to Rancher using this manifest, saying, hey, Rancher, I want to create a node driver. It's going to be called Oxide, and here's all the information for that plugin and where to find it. Then once I have that deployed to Rancher, I can create a configuration that the plugin actually expects. So for example, in this case, the plugin is expecting you to pass it the boot disk, the project to create the instance in, and an SSH user. So I can create that configuration. And then with that configuration, I can actually create a Kubernetes cluster. So this is saying, hey, create a new Kubernetes cluster called Oxide K8 cluster. Use that Oxide config that you just created, which will use the actual Oxide node driver plugin, and that'll create the instances and create the cluster. And boom, you have your Kubernetes cluster with not much of a headache there. And again, I know this is a Kubernetes manifest to deploy it to Rancher, but you could have deployed this via the Rancher UI as well. So the code for this is at oxidecomputer/Rancher machine driver Oxide. And the fun fact about this was initially developed by an Oxide customer, and Oxide took over maintainership. This was actually my first project when joining Oxide. It was, hey, Matt, here's a pull request with this Rancher machine node driver thing. Go have fun, go look at it, see what's going on. And I did. Another way to manage Kubernetes clusters is via Omni. So I'm going to talk about the Omni infrastructure provider. An Omni infrastructure provider is made by Side Arrow Labs. So it's a way of connecting Talos Linux machines to Omni for automatic machine management. Talos Linux it's a Linux distribution that is sole purpose is to be run as a Kubernetes node. So it has all of these sort of features and mechanisms to spin up Kubernetes components, be managed via gRPC API, and so on and so forth. And Talos Linux's sort of stance is like a secure, small, minimal operating system. And there's no SSH, there's no shell, and you're supposed to manage it via gRPC calls. When you spin up a small like home lab cluster for Talos Linux, you're generally going to use their CLI tool, and that's fine. But when you're managing like a fleet of Talos Linux machines, you want to use something called Omni, which is also made by Cytera Labs, and Omni manages many, many Talos Linux machines without you having to use like the CLI and whatnot. So when you create an infrastructure provider for this, you're telling Omni, hey, here's how you can create Talos Linux instances on Oxide. And there's two types of providers, static and dynamic. Static says create an instance on your cloud provider and never destroy it once it's not in use. Just keep kind of wiping it clean. It's kind of better for bare metal than cloud, personally. And then there's the dynamic provider, which is, hey, anytime someone is in Omni and creates a Kubernetes cluster, spin up the instances on demand and connect them to Omni and create that Kubernetes cluster. And that's the one we implemented for Oxide. So much like the other plugins, there is an interface to implement, but I find the interface here much simpler and more ergonomic than say the cloud provider, than say the cluster API or the Rancher node driver or things of otherwise. This is a pretty nice interface. You have two methods: provision steps, which tell you the steps to follow to create an instance, and the instance is specified by the T type there, the generic over T, and then deprovision. How do you destroy it, right? How do you get rid of it? So what do? An Omni infrastructure provider really is meant to do a couple things. One, it's meant to generate what's called a Talos Linux schematic ID, and that holds all of the kernel parameters and configuration that the Talos machine should be started with. Then the plugin's supposed to download the Talos Linux image, upload that image to Oxide, and then start the Talos Linux instance with the correct cloud init user data so that it can connect to Oxide. That's really all it does. And if you look at the code, if you look at the steps for it, this is all it does. How do you deploy this thing? Well, again, once you implement the interface and build the binary, you can just export the correct environment variables to connect your binary to Omni and also to connect your binary to Oxide, and then just run it. So here I am just running the Omni Infra provider with an example flag. Using it and installing it into Omni is pretty simple. You just go into Omni settings, you create an infrastructure provider, you give it an ID, and then it'll give you that Omni endpoint and key that you can pass to your binary. And once it's all running, you'll see it appear in the Omni UI. From there, once you use it and you actually say, create me a Kubernetes cluster of maybe one node or whatever, it'll actually spin up, talk to Oxide, create an instance, connect it to Omni, and then you will see the instance listed in the Omni UI. So here's just an example instance that is listed in the Omni UI. But if you look at the sidebar here, you can see that it was an auto-provisioned instance via the Oxide Omni infrastructure provider. The code for this is at oxidecomputer/Omni Infra Provider Oxide. At the time that I recorded this initially, or that I gave this talk initially at All Things Open, this was still under development. And yeah, I told people to see the pull request. I've since merged a bunch of things to main or to the default branch, and now the code is there for you to see. It's still not what I would call production ready. I'm still making changes, but it's there and you can take a look at it. I actually really enjoyed the developer experience building this provider. There was a little bit of an initial ramp up because there was not a lot of information about Omni infrastructure providers, but after I ramped that up, the developer experience was kind of great. And the Cytera Labs maintainers were very, very friendly and nice in this linked discussion here on Omni 1633. We found a bunch of bugs. We found answers. It was a great time. What about non-cluster management things, right? What about something like a CNI or a container network interface? Did we make a plugin for that? Well, the CNI plugin is responsible for a few things. It's responsible for container networking in the whole, but the way it does that is a CNI's sole responsibility really is to configure the network interfaces on a given Kubernetes node, with the goal of making sure that pods running on that node or containers running on that node can have the correct network connectivity. That's basically all a CNI is meant to do, but the act of doing that can be complex with different ways of managing network interfaces and overlay networks and so on and so forth. It can just be kind of complex there. And there are many, many third-party CNI plugins available that a lot of the public cloud providers use directly. So at Oxide, we decided to also not implement the CNI plugin at this time. There are great third-party CNI plugins, right? There's Flannel, Calico, Cilium. There's a bunch of them out there, and most major cloud providers use them as well. But perhaps we will revisit this in the future. And there's some interesting points around here that I won't go into super detail here, but we have the ability to really kind of eliminate some of the networking cruft on Oxide when you're running Kubernetes. Like we can use our VPC networking directly rather than some sort of CNI. But that's another conversation for another day. We haven't implemented it now. We are deferring this to some future when we can revisit it. But there's another plugin, and this is a device plugin called the Container Storage Interface. And the Container Storage Interface is meant to expose arbitrary block and file storage to your containers. So, for example, when you run containers in Kubernetes, they spin up, they run their image, and they can serve workloads. But when they spin down, there is no persistent image by default. You need to configure some sort of CSI plugin to have persistent storage for your containers. Think for things like databases and such that need that stateful persistent storage. That is where the CSI comes in. If you want to deploy a CSI, you do this. You create a CSI driver type or kind, and you tell it what its name is and what the spec it should be. So for here, we're saying, please create a CSI.oxide computer CSI driver, and attach is required, pod info on mount is not required, and the FS group policy is file. So you give it some of that spec. Then you create what's called a storage class. A storage class is what sort of type storage is available through this CSI plugin. And we have one storage class here called the Oxide disk storage class, and it's using the CSI.oxide computer provisioner. Once you have that running, once you have a CSI plugin running, you can create your persistent volume claim, request storage, and it'll go out to Oxide and get storage for you and make a disk, attach it to a Kubernetes node, and you're good. And if you're wondering why I didn't show you the code here, it's because at the time that I recorded this a few weeks ago, at the time that I gave this talk live a few weeks ago, the code was still under development. It still is, right? Even today, the code is still in development. It is at Oxide Computer /Oxide CSI plugin. If you click that link, it'll be internal. You won't be able to see it, but that's where we'll be when we make it public. So this is all still under development for now, which is why I haven't showed you any sort of the interfaces or code behind it. But we do have this running, and I've demoed it actually in a Cloud Field Day presentation from a few weeks ago from this recording. Go check that out. If you search Cloud Field Day Oxide, you'll see it. And I did demo the CSI plugin working. But again, still internal only for now. It'll be public soon. We're just working through a couple blockers. What I like about this plugin is it solves this write amplification problem that we have on Oxide. And I don't want to say that in a bad way. It's just that Oxide's storage is replicated in 3. So when you create an Oxide disk, the data for that disk is replicated 3 times for redundancy, right? So you don't lose your data. So when you layer like a third-party CSI on top of the Kubernetes cluster, like Longhorn, it usually manages its own replication. So now you have replication at the Longhorn layer and replication at the Oxide layer, and like that's like a write amplification problem. So if we develop our own CSI plugin, which is why we want to do it, it solves that. But there are a few blockers that we need to go through and fix. One of it is currently there is no hot plug attach detach for Oxide disks. We require that the instances are stopped and then you do an attach detach. That obviously is not acceptable in a Kubernetes cluster. Forgive my dog, it's late. That's obviously not possible or recommended in a Kubernetes cluster because you don't want to stop your instance or your node to attach a disk. That can cause cascading sort of pod reshufflings that you don't want. And another blocker is that instances today can only have a maximum of 8 disks attached. And we need to probably be able to attach more than that if we want to serve the needs of our customers. So out of developing all this stuff, what lessons did we learn? First is the bootstrapping problem. And this is what kind of steered me away from the cluster API is like, how do you create the first thing, right? How do you create the first dependency that you need before you can get going? This is a big problem in software in general, but definitely in the Kubernetes world. For example, with the cluster API, Kubernetes has to exist before you can use the cluster API to provision more clusters. So you have that sort of bootstrap problem there. And there really is no right answer here. Not going to lie to you. You just have to document what your requirements are and what your dependencies are and make design decisions to limit them if possible. Again, not knocking anything, but that's just the reality of it. Then there's another lesson where a lot of the Kubernetes interfaces were built on public cloud assumptions. And when you move to on premises, these assumptions aren't always true. For example, right now, at the time of this recording, Oxide doesn't have a concept of a region or a zone or even instance metadata, like an instance metadata service. So when you have Kubernetes integrations that specifically rely on these or expect these things, for example, region and zone is one of them in the Cloud Controller Manager. If you look at the code, the metadata method expects you to set region and zone for the Kubernetes topology. What is I supposed to set them to in Oxide when we don't have that? So things like that, where these public cloud assumptions kind of built up, that was a little frustrating and a lesson learned. And quite frankly, like, I'm not blaming the public cloud or anything. That's the integrations that we've all kind of settled on as an industry. But to me, as a developer for these integrations, it was unclear of what I should be doing when these assumptions were missing. Obviously, the answer is make Oxide support regions and zones. But when I can't do that today, what do I do? Right? And that was sort of the lesson learned there. Speaking of some Oxide limitations, the Oxide product is growing, right? We're solving a big problem in the industry. Co-design hardware and software to have your on-premises cloud computer, that's a big ask. So we are missing some features today. And that's fine. Like, I'm not saying that to knock it. It's just we are missing things because we had to prioritize other things. For example, we don't have a load balancer in the product, and I already mentioned that. So that means I can't implement the load balancer controller without doing something sort of kind of hacky or outside the beaten path. There's no concept of resource tagging. Kubernetes clusters on cloud providers tend to make use of resource tagging to isolate cluster resources from one another in the same sort of shared environment. There is no instance metadata service. So if I wanted to retrieve information about an instance, how do I do that? Right? I need an API token to hit the API directly rather than doing some sort of instant metadata service. And for authentication, I have to have an API token. I can't use instance identity because we don't have that yet. And that's something we're looking at building in the future as we build up that sort of full root of trust for Oxide, but it's not there today. So these limitations were documented, they were discussed, but also I worked around all of them for now, and I documented them in each plugin when necessary. Speaking of documentation, one of the biggest lessons learned and kind of frustrations for me is the lack of documentation in this Kubernetes ecosystem as it relates to plugins. And I specifically left this slide like this, click to add text, to kind of be a little funny about this, because that's what I felt like when I went to look at the various Kubernetes documentations for plugins. This is what I felt like. I felt like there was no documentation there. I had to read all the code to figure it out. And it was just kind of frustrating to me as a developer when you have to develop, different plugins across different ecosystems. There is no like, here's an example plugin that we created to showcase development. It just like really wasn't there. There's some code here and there that you have to piece together. But if it wasn't for like AI and like just sitting down and trialing error and things, I would have kind of had a bad time. So in summary, like the integrations ecosystem in Kubernetes is pretty poorly documented. And I don't say that to like, stick at it people. Like, no, I'm not saying that in a bad way. I'm just saying that's the reality that I faced. And it was tough for me to implement some of these things because the documentation was kind of minimal. There's pretty minimal examples with kind of not useful comments. Everyone is just saying, go look at AWS. Like, I don't want to look at AWS's code because it's kind of very different than what I'm looking at. And I ended up looking at a few different example codes out there to really piece together what should be done for Oxide. And even when I asked people that were Kubernetes experts or whatever, quote unquote, they were still using outdated patterns. So it's a lot, right? There's a lot of out-of-date documentation where it was just hard for me to really get up to speed as I'm context switching. And the point there is, I know integrations are tough, right? But they're super critical to the user experience. So document them. Integrations are that point where your customer is interfacing with your product it should be very nicely documented so that people like me can go create the integrations that are needed to get my customers using your software on Oxide. And here's some closing thoughts. I learned a ton, right? And this is not me. I'm like, again, I know I complained a little bit about in the documentation phase, but I learned a ton. I learned a lot about Oxide. I got to use the product in different ways, understand the code base, understand the API a little bit better, and I got to learn more about Kubernetes. So much so that I read the Kubernetes documentation cover to cover on the website, and that I don't recommend that to anybody, but I did learn a ton about Kubernetes, how things work, and it really did feel good when you like deployed these integrations to a Kubernetes cluster and it just worked. Like the first time I got the Cloud Controller Manager working and that taint was removed, I was like, yo, this is great. So I learned a ton. I also built up a lot of user empathy because I understood that there's developers out there making these systems and making plugin interfaces, and I have empathy for them, although I do want to push them to do better documentation. But even the users, right? There's users out there that aren't on AWS and want that sort of cloud familiarity with their Kubernetes workloads. And me building, or my team at Oxide building these integrations for them, really helps build that user empathy and get them understanding like where their problems are. So that was really, really fun. And honestly, it made me realize that things aren't as complex after you do a bit of prototyping and sort of trial and error. Like I said, when I got that Cloud Controller Manager working, I was like, wow, that's actually not as bad as I thought. And go look at the code. It's really not bad at all. It just took a while to get there. The other thing I'll say, and this I was actually thinking about this today, so it's funny that the point is here. Context switching is so difficult and very costly, but it's necessary, right? If I'm creating the Cloud Controller Manager and the Rancher node driver and the Omni infrastructure provider, sure, those are all related to Kubernetes, but they're different context switches. And it's hard to like go from project to project and context switch and remain super productive, right? That's hard. So I often got people saying like, "Oh, Matt, I built a prototype of the cluster API. Why didn't you do that?" Like, it's because I've been managing 3 integrations and you got to focus on one. So like that context switching, and that's the nature of this role at Oxide, to be clear. But that context switching is difficult, and understanding that and knowing how to work around that is very crucial. Also, we've written up RFDs about all of the stuff that we spoke about here today in this talk. You can find them at the public RFD site for Oxide, RFD 493, which is the initial Kubernetes integrations, where I document the Cloud Controller Manager, the cluster API, the CSI, all that stuff. And we have a specific Oxide CSI plugin, RFD 595, where we discuss more of the implementation of the CSI plugin. So if you're curious about that, go check that out. All of the RFDs and all of the work that my team at Oxide is doing, or the team that I'm managing at Oxide is doing, I'm pushing for it to be open source if it's not already. And luckily, the nature of Oxide and the nature of what we're working on at the integration layer is very, very friendly to open source. So everything that I spoke about here is open source. The information's out there, the code and the RFDs, with the exception of the CSI code, because it's just we haven't clicked the public button yet. Oh yeah, I should probably tell you a little bit about me. I mean, you all know about me on YouTube, so you already know who I am. But for a little bit more background for those that don't, I was the first solution software engineer hire at Oxide Computer Company. So I started a new team there, a team of 1 at the time. It was me. And the whole idea was that we're spinning up this sort of generalist team with specialized scope. And what I mean by that is the teammates on this team have to have the ability to work across a variety of different things, right? That context switching that I was talking about. So that's where the generalist comes in. But the specialized scope is focus on customer problems, right? Make sure that the ways that customers integrate with Oxide or interface with Oxide, make sure those areas are well understood and that there's tooling and code in there to make it very useful. So what do? We own things like the Go SDK, the Terraform provider, Packer plugin, OpenTelemetry plugin, Grafana plugin, all the Kubernetes plugins. So we own that sort of integration layer between Oxide and other systems to make that customer experience better. And now today, as the time of this recording, I lead a team of 4 people, myself and 3 others. I also have an extensive site reliability engineer background, so I've been very keen in this reliability and systems performance field. And if you want to find me online writing and speaking, I blog on my website, matthewsomber.dev. and I podcast at fallthrough.fm. With that, thanks.